So welcome everybody to our lecture on trustworthy federated learning within our course on federated learning. Before I start with the actual lecture, I would like to take questions. Does any one of you have questions? You can also post questions in the chat, those who are in Zoom. I would like to briefly discuss one question that I got, a very good question from a student in the feedback, which was, how can we generalize the analysis that I present on this course? And this analysis mainly applies to linear models. So if I briefly sketch our setup, that of course you're all familiar already. So we have local data sets, which could be generated by a variable or a smartphone or by a weather station. And we learn a local model, and this local model is a linear model. So we learn the weight vector or the parameter vector of a linear method. And then you get nice bounds in the lecture notes that tell you how far is the learned parameters away from a true underlying parameter. So we get all kinds of upper bounds. I provide you some upper bounds. And in these upper bounds, how does the local data set enter these upper bounds in the analysis? So these local data sets, they consist of pairs of feature vectors. So here, this is the ith data set. Let's say this is the first data point. And then we have a label. ith data set, first data point, this is the label. And we can stack the feature vectors into a matrix, into a single matrix, which I call the feature matrix at the ith data set. Okay, and in many of these bounds, you see not the data points themselves, but you see properties of these products of the feature matrix. So you see feature matrix of the ith data set transposed times xi. And I used to denote these matrices using the letter Q. This is this matrix Qi. It's a quadratic, the product or a quadratic form of the feature matrices, so to say. So in these bounds, in all this analysis, the local data sets enter via properties of these matrices. And do you remember what type of properties enter into their bounds, into the analysis? Is it the shape of the matrix? Yeah, okay, the shape is the number of features. It has also a role, but what are the characteristics of these features that enter into these bounds? What did I tell you in the beginning, in the first few lectures? What is the most useful result in linear algebra in the whole course? Because this is a positive semi-definite matrix, as you can easily show. So it's also symmetric, so it's symmetric and positive semi-definite. And what can we do with a positive semi-definite matrix always? We can decompose it. We can decompose it into spectral components. So we have a spectral decomposition. So the spectrum, which is another word for the values of the eigenvalues. The eigenvalues are the important thing. So the eigenvalues of this matrix, the lambdas, the eigenvalues of this matrix, they define or they enter into the upper bounds, into the analysis. They enter into the characterization of convergence speed, so into the computational properties of the federated learning algorithms, and they also enter into the statistical properties. So how far is the learned parameter vector that I learn by solving GTV minimization, how far is this away from the true parameter vector? So this is related, this is called an estimation error. And we, in the lecture notes, you find bounds on this estimation error, so true underlying parameter vector minus the estimated parameter or learned parameter vector, and then you get a typically long bound, long expression, complicated expression, or not so complicated. But the important thing is that in this bound, the local data sets enter via the eigenvalues of this matrix Q. So why do I now tell you all this? Well, once you have a nonlinear model, what will be different is that this loss function, so we evaluate the quality of a weight vector using the loss function. And it turns out that this Q matrix here is the Hessian of this loss matrix for linear models. So when you have nonlinear models, you need to compute the Hessian, and the Hessian is then not given as this nice quadratic form using the feature matrices, but something else. But you can compute the Hessian using numerical approximation. So roughly, it's a very rough direction. You can generalize the analysis, or you can start the generalization of all this analysis in the lecture notes to nonlinear models by trying to replace, whenever you find this matrix here, this matrix Q, replace it with the Hessian of the loss function. And I just looked around a bit, of course. What is a nonlinear model that is currently very popular and media hyped? A deep neural network structure that you hear about a lot in the media. What is used in ChatGPT? What structure? Transformer networks. So let's see if we are lucky. Hessian properties of transformer networks. Of course, I have tested this stunt before. So yeah, there's a recent paper. Why transformers need a Hessian perspective. So Hessian doesn't mean it comes from the state in Germany, but the Hessian is the Hessian matrix. These are the second order derivatives organized into a matrix of the loss function. And this paper seems to try to, yeah, here is the definition. These are the mixed partial derivatives of the loss function. And if you use as loss function the squared error loss and the linear model, you obtain what you get out of this Hessian is exactly the Q matrix, this feature matrix transposed times feature matrix. So for the linear model, this Hessian reduces to this Q matrix that I use in the bounds. And it seems they provide some kind of characterization for these eigenvalues. I didn't read it in detail, but this would be one direction. But this is hard. So this is, I would say, clearly beyond the scope of a typical master level course. But yeah, maybe if you're interested, I'm always all ears if you want to pursue this in a research project, and maybe we make a nice paper then out of it. Okay, any questions at this point? So one way to generalize all this analysis in the lecture notes, which is deliberately focused on linear models, because you get somewhat manageable expressions. So let me see one example for this analysis. One example, where did I, here in the federated learning principle, when I present upper bounds. Yeah, here, for example. Oh no, here's no, this is too simple. I avoided here the estimation error for some reason. Lambda 2, where do I get this lambda 2? Lambda x. Yeah, I think for the gradient methods, when I analyze the gradient methods for GTV minimization, here we have the, yeah, here. Here, all kinds of eigenvalues, different types of or different choices or different eigenvalues that are used of these Q matrices. So to generalize all this analysis, which strictly speaking only applies to linear models, you have to replace this Q matrix by the Hessian. And but the Hessian of a transformer network is a matrix of size, number of parameters, tunable parameters. So roughly how many tunable parameters do you have in a modern deep neural network? Millions or billions. So this is highly non-trivial, how to characterize the eigenvalues of such large matrices. I guess you need to kind of pull all kinds of mathematical tricks, which are, as I said, clearly beyond the scope of this course. Yes. Any questions? If not, then quickly check also the chat. No, in the chat, also no question. So today, I want to talk about the main component of federated learning. So we have talked about several components of federated learning so far: data, local models, loss functions. Then we have bound them together in a principle called GTV minimization. And what you get is, as a result, when you solve GTV minimization, you get model parameters, so local model parameters. And at some point, we need to do something with the model parameters or with the learned model parameters. So the main component of federated learning is the human user. For example, me, I use a federated learning system to give me optimal predictions for the weather tomorrow. So maybe some of you have tried federated learning algorithms on weather data, for example, in the assignments. So one use case is to deliver weather predictions to a user. And in this regard, there is now growing awareness that we need to regulate, we need to somehow set rules for how these systems can work. Because these are very powerful systems, very powerful technical systems, but which can also cause a lot of harm. Do you know another example for powerful technical systems which can cause a lot of harm, but we use routinely in our everyday life? What are powerful systems or technical systems, technical objects that are very useful, but also very dangerous, and we use in our everyday life without being worried too much, or we come across them, or hopefully not come across them at safe distance. So cars. I mean, cars, it has 1 ton, a moving mass at 1 ton at 50 kilometers per hour. I guess you will not survive if it hits you directly. Very dangerous, but I guess you are not paranoid when you get out of this building and see cars. So we somehow managed to regulate the use of cars, that it's safe. Yeah. So, but similar, and I mean, the difference here is it doesn't look so dangerous. It looks so innocent. It looks like a cute little toy that we give our 10-year-old kids and which then are all the time hooked on the smartphone. But it can be actually much, much more dangerous than a car. It's just not so obvious to us in our physical experience and in our, how we are used to handle risks or dangers. So the European Union now took action a few years ago already and defined 7 key requirements for trustworthy artificial intelligence. And one important subset of artificial intelligence is machine learning. And within machine learning, we have many systems which are actually federated learning systems. So whatever they tell us about, or whatever law there is about AI, applies also to federated learning because it's a special case of AI, of an AI service. Okay, so I would now like to walk through these 7 key requirements, and you will see that this is not really my home turf. So I must say I would have liked to give this lecture way earlier because, again, the main component of all federated learning is the human. It's a tool for us. It's our assistant. It's not our commander. We are not working for federated learning. We need to have federated learning working for us. However, my training and my expertise is in the technology. So how to develop convergence rate bounds and how to develop estimation error bounds. That's why I did lectures on those first. But I really am passionate to tell this, to bring this more into the focus, this human perspective or this human-centered perspective. So, and the first key requirement, for example, is human agency and oversight. So I cite here directly from this document from the European Union, which I have also shared on Slack and by email, which says AI systems should support human autonomy and decision-making and have respect for human autonomy. And here, for example, this is also related to the notion of human dignity. So we should not be manipulated or we should not be instrumentalized. And this is actually already at risk, or I would say, violated to a large degree by federated learning systems that are used to make predictions about what to consume next, what to show us next. So we could use a GTV minimization method to learn a linear model for me. And the prediction of this linear model is, what's the percentage that I would like to watch now this new video, yes or no? So these predictions are turned into something showing up on my phone. And this showing up on my phone might steer me, might manipulate me, and violate my dignity. So this should be taken into account by you. You will be most likely then the one who decides what is used as a quantity of interest. So do we want to predict user behavior? Should we predict user behavior, or should we not try to predict it too accurately? So this is something that the federated learning or machine learning engineers to a large degree will have under their control. And they should take care that it's not used to really manipulate people. Yeah, any questions at this point? Yeah, to support human autonomy and human oversight, the models that we train should be simple. So simple is good because it allows the human somewhat to get an intuition. What is a simple model, in your opinion? What could be a simple model, a simple machine learning model? A linear model, yes. That's why I took it, of course, or in my examples, because it's also good for the human agency and human oversight, because we human might have some understanding or some intuition how a linear combination works. However, this is not a precise definition, because a linear model using 1 billion features is not interpretable. It's not simple. For me, it's completely opaque. A linear model where you feed in 1 million pixel red, green, blue values, and where all of the weights are non-zero, it's hardly interpretable. So this is, of course, a bit subjective or up to convention, but a linear model with a few features, let's say 5 or less than 5 features, is often considered simple. Another example for models that are referred to as simple is decision tree. Decision tree with a small depth. Okay, then for human oversight, it's also important to continuously monitor the federated learning system. The federated learning algorithms that I presented in earlier lectures, they can be used in a one-step, in a single-shot setting. So you collect the data sets, you set up the optimization algorithm, and you train the local models. And then you use it all the time. But this might be not useful for several purposes. First of all, the data characteristics might change. So you might have a different distribution of data points at another period of time. So you should then retrain the model. So it's then always more preferable to continuously update the model. And yeah, by the way, could you think of an optimization algorithm that easily allows to update model parameters if a new data point comes in? Something that a new data point comes in, it estimates a gradient and does a gradient step. So gradient methods. So you can formulate, yes? Yes. Sorry, could you repeat the question? Was it? Yes. 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 It's a form of trial and error. So let me show you here with the gradient methods or even the gradient step for GTV minimization. So this basic gradient descent works by updating the local model parameters via 5.9. And in 5.9, we have here the whole data set, so the feature matrices. But you can replace this gradient here by an estimate, and this estimate consists of one data point, which is the new data point. So this one advantage or conceptual advantage of this gradient methods is they can easily be adapted for real-time operations, for continuous operation. They are then called online gradient descent instead of gradient descent. Okay, so again, gradient descent in hindsight was a good choice. Also regarding trustworthiness. Okay, so key requirement 1 was human agency and oversight. Continuous monitoring we discussed. Yes, that's what I had in mind about key requirement 1. Any other comments or suggestions? What could you think of should be taken into account for human to ensure human agency and oversight when we implement GTV minimization methods? Yes. Yes, very good, very good. So the comment was, if you want to, if you do continuous update on new training, on new data, you should somewhat make sure that the new data that comes in is also trustworthy or reliable or corresponds to the underlying data generation process and is not manipulated. So this is also related actually to key requirement 2, technical robustness and safety. So AI systems, and in particular federated learning systems, should be developed with a preventative approach to risks and in a manner such that they reliably behave as intended while minimizing unintentional and unexpected harm. For example, if the data distribution changes or someone fiddles around with the data points, with the new data points that come in, some cyber attackers change the data. Yeah, we'll talk about more towards the end of the lecture, because technical robustness, this is closer to my home turf, so to say, because it's related to studying the behavior of. So let me now go again to the whiteboard. How much does the learned parameters change when we change a bit data points? So one form of robustness is robustness against perturbations of local data sets. And you can develop nice bounds, again, for linear models that tell you once you perturb the data point, you will learn a new parameter vector, of course, because you have a new data set. But this difference can be controlled by using specific types of features, for example. Okay, so this is one important aspect of robustness. How sensitive is the federated learning method against perturbation of data sets? And we will have, yeah, by the way, we will also have a dedicated lecture. I guess the last lecture will be on cyber attacks, or data poisoning attacks and defenses. So regarding robustness, what else did I want to say? Yeah, they should also be robust against failures in the computer. We have, as computer, in federated learning, as computer, we use our smartphones. Yes? Yes. Sure. So you can measure the size of, when a new data point comes in and you calculate the new gradient step, the size of the gradient influences or is related to the robustness. So if the gradient is not too large, then there will not be much change. Sure. So regarding robustness, we also have to take into account the computing infrastructure. And the computing infrastructure is, for example, all our smartphones in this room. Let's say we have all our Bluetooth on, we all trust each other, we allow Bluetooth connection with each other. All our smartphones, together with the Bluetooth connection, form a computer all of a sudden. But this computer behaves very unreliable compared to this computer. how often did you have really that some computation went wrong? Like on the lowest level, the CPU made a summation error. This never happens. And this is one of the cool things about digital computers. They are so reliable. They always do the same computation, unless really something hits the computer. But in this case, for federated learning, we have highly unreliable computation. So all the time, my smartphone now runs out of battery. Somehow the Bluetooth connection is turned off. And a federated learning algorithm must kind of tolerate all these imperfections. And it turns out, by the way, that gradient methods are a good candidate to obtain such robust distributed optimization methods. So I will talk a bit more about this later then, about asynchronous optimization algorithms. Okay, next key requirement, privacy and data governance. So this is related to a comment before that it's easy to write down a feature matrix on my paper and to analyze a federated learning algorithm using some characteristics of a feature matrix or feature vectors. But how can you be sure that the feature vector that you really read in your computer is actually the feature vector you are thinking it is? So this is related to data integrity. Data integrity is an important component of data governance. So you should always ensure that the data that you read in is really the data that you expect it is. Like you really get the temperature measurements from fMRI. But to some extent, you must trust the data source. Because in federated learning and in machine learning in particular, the idea is you learn something from the data you read in. So if you're 100% paranoid, you don't trust any data, you cannot do machine learning. You cannot trust any data that you get. So you must trust some data sources to start learning and then use this knowledge to evaluate other data sources if they could be trustworthy. But if you don't trust anything, so at the beginning you need to take a risk. You need to use some data to start learning. Okay, then also we will have a separate lecture on privacy protection. So this penultimate lecture will be on privacy protecting measures, or how we can protect the privacy while still learning useful parameter vectors using GTV minimization. And one basic or simple idea is to add noise, to perturb a bit the intermediate results of the federated learning algorithm. And this is called differential privacy. And it allows for a trade-off. So we can have more privacy protection by adding more noise. But of course, adding more noise to your computation will somewhat naturally deteriorate the estimation or the accuracy of the model that you learn. So there will be a trade-off between privacy protection and accuracy or statistical properties of the trained models. Okay, let me see if there are any questions in the chat. No. Next key requirement for transparency. Transparency includes traceability. And this means that you should precisely document all the design choices for a GTV minimization-based method. And this you practice in the project. So we will have soon a session, an info session about the federated learning projects. And one part or one key requirement for this federated learning project is that you write a report. And in this report, you must clearly specify what are the local data sets or where are they from, the sources, what are the local models, and what are the loss functions you have used. Beside those, also the empirical graph, or how you constructed the empirical graph, is an important design choice. Yeah. And beside documenting all these design choices, you might also, or you should also then periodically store intermediate results of the computation, like current model parameters during or after a gradient step. This is related to logging, or it's known as logging. Yes, yeah, communication. This depends on the use case. But you should maybe also inform users about limitations of the system. So provide some measure of uncertainty about the prediction. As an example, when you wait for the bus, at least a few years ago, I remember there was not only a prediction for the time of arrival, so when will the next bus come, but there was also a measure for the uncertainty about this estimate. And this was very useful. So this was in the form of a bar diagram. So the more the bar, the more certain it was, or vice versa, I don't remember. But you had not only the prediction of how many minutes does it take that the next bus comes, but also how certain are we, or is this transportation organization about the prediction. And one way to get such an uncertainty measure is to use validation error. To tell the user the validation accuracy was 60% in a binary classification problem. So not too high. So the user might then know, maybe I should not rely too much on this prediction that I get from this federated learning system. Okay, and then another component of transparency is explainability, which I will talk about also later a bit more, because this is actually a subject of my current research, explainable federated learning. Okay, then next, are there any questions at this point about these 4 key requirements so far? Okay, then key requirement 5, diversity, non-discrimination, and fairness. Yeah, one example that I like to show here is not included here. So we might use machine learning or federated learning to predict a compensation for a job candidate. So how much compensation should we offer to this job candidate based on his or her qualifications and job interview performance? So another example could be, should you grant a loan to a customer, bank customer? So credit score prediction. And here we could ensure fairness by data augmentation, by saying, okay, I have some training data for which I know what we should offer as compensation. And this is based on some features. And then we want to make sure that this prediction does not depend at all on, for example, only the gender. So all other things being equal, the compensation that we offer should not change if we change the gender of the person, of the candidate. Or the credit the credit score should not change if we flip the ethnicity or the religion of a bank customer. Although I hope they don't know the religion in general. Yes. Yes, so this is a cartoon. This is not a quantitative scatter plot. Yeah, you will have gender. I mean, you could also represent gender by a numeric quantity. I don't know how to do it reasonably, but why not? There's a spectrum. Yeah, but this is a cartoon. Gender is typically, as I would use a discrete variable for it. But still, you can augment data points by flipping discrete variables. Yeah, but you might then not use a linear model that is hinted at here, but a decision tree, for example. Good point. I might revise this figure. Yes. Any other comments regarding fairness or diversity? And again, this is something you might be soon. I don't know about your career plans, but maybe not too far away from this day. You might sit at a company and develop software, or machine learning software, where it is at your hands to ensure fairness. And one simple way to ensure fairness, maybe then you remember the course by Alex Jung. One way to ensure fairness is a simple data augmentation. Just perturb the features that you do not want to have a direct impact on the quantity to predict. Yes? Yes, yes. So good point. Good point. And this is related to data minimization. I think I discussed this in this key requirement for privacy or data governance. So if you know per se that a certain feature is irrelevant for the learning goal or for the task that you want to solve with machine learning, actually, then you are not allowed to use it. You're not allowed to use it. So this is called data minimization. And from this perspective, yeah, you should not use gender at all. But in some cases, it might be useful to use the feature, but to make sure you don't overly rely on it. So there's some transition between this using the feature freely and don't using it at all. You might use it to some degree. And actually, there might be some guidance how much weight you want to give that sensitive feature. Yeah. Okay. By the way, did any one of you work or had to do with an audit of a machine learning system with some company? No. So this might be one of your tasks in a job as a machine learning engineer, to assess all these requirements or check if they are satisfied by your system or your company's solution. Okay, then key requirement 6, societal and environmental well-being. Yeah, I mean here, what I hinted to in the beginning, societal well-being. This includes, of course, well-being of individuals, and the well-being of individuals can be clearly affected by recommender systems that use federated learning to train a personal model, one model for Alex. And the predictions of this model are, what should I show him to maximally catch his attention? And then Alex ends up 12 hours a day in front of the smartphone, being totally addicted. So clearly hurting my well-being, or my well-being suffers. Not good. But this is only one special case. That you could do much more. I mean, it's always what I say, these social media apps combined with federated learning or AI, I think are the wet dream of any information warfare expert of any secret agency from the last century. Because you can now brainwash people on an individual level with a channel that is open almost all the time. I mean, some of us even might go to the toilet with the smartphone. So you are permanently exposed to information, and this information can be used to steer you and even to steer whole societies. And I have heard about cases where this spreading false information or information campaigns could even result in social unrest or even genocides. So this is clearly one big threat of federated learning technology. And again, you as a machine learning, as a graduate from Aalto, working as a machine learning engineer, to a large degree, it will be in your hands to not allow this to happen, to not allow federated learning systems to be abused to make people crazy and trying to kill each other. Okay, so societal well-being, very important component. Environmental well-being, at least as important. In this regard, I want to point out that all the federated learning algorithms that I talk about in this course, they need to be implemented at some point. And how do you implement them? On a computer. And a computer in each clock cycle needs energy. Every computation needs energy. And also this distributed learning algorithms, these federated learning algorithms require transmitting information over wireless channels, for example. This needs energy. So you might end up with using a lot of energy for the whole federated learning system. And again, there are then different design choices. Some design choices result in more energy usage. Other design choices result in less energy usage. And also indirect effects like that the battery lifetime is maximized. You need less battery or less battery capacity. So it might be also good to make very little use of battery power. As I understand, battery production or battery energy has also not an optimal environmental friendly footprint, so to say. So again, it's to a large degree in your hands how environment friendly the resulting federated learning system will be, by using clever designed algorithms that need only 10 iterations instead of 100,000 iterations that run 100 times longer on a big computer. Okay. Yes, the last point is empty. I didn't really find what to say here. Accountability. Just here quote these guidelines from the European Union. Mechanisms should be put in place to ensure responsibility and accountability for AI systems and their outcomes, both before and after their development, deployment, and use. So are there any suggestions? What could be a way to make sure that or to ensure accountability? What could that mean? Yes. Yeah. 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 Yes. Very good point. So accountability refers also to documentation. Everything should be documented precisely, such that any claims or statements about accuracies are reproducible, and also any trade-offs that have been made explicitly or implicitly should be discussed. Okay. So that was a quick walk through these 7 key requirements. And yeah, I really would like to have you remembering this, at least there are key requirements. Yes.
There are so many players, the algorithm, and as we discussed, like the transparency, that you don't very much even understand the linear model, and it's giving some recommendations or whatever. So like, who is the person, the last engineer or the business owner or the designer or the user or some combination, and how is that like coverage?
Yes. Yeah. Yeah. Yes. Good point. So it should be somewhat clear the one who is responsible at the responsible list. And I didn't mention it, but for data governance, for example, there's the notion of it might be required to designate a data protection officer. So there are certain roles defined by this regulation, like a data protection officer. And I guess at least this should be clearly documented for having accountability. Yes, comment? Yeah. Mm-hmm. Mm.
Still a matter of research, who is going to be held responsible. But the general idea is that the company or entity that defines the means and measures on how to, like, what is the aim and how to introduce the aim and how to get to the aim, which kind of data is connected. Usually they are seen to be controllers in the concept of.
So also part of this accountability, I would say, is when you have a federated learning system that is used, for example, on a social media app like TikTok, you make clear who owns this or who operates TikTok. So I like to always ask when I give guest talks in high schools, and do you know who owns TikTok or who operates TikTok? And they are always surprised because they don't know. So does any one of you know which company runs TikTok? Sorry? ByteDance. And where's ByteDance from? Is this true? I don't know. I'm not an expert because I don't know where they are registered. I guess there are tricks. They are somewhat in Luxembourg. Oh, no, I'm on record. I might not say anything. Oh, in Austria registered for tax reasons. I need to cut this then. Okay, before I put it on YouTube. Don't want to harm my career prospects. Okay, so then we have, yeah, any comments or questions still to the 7 key requirements? I strongly encourage you to read over this PDF brochure or a white paper that I shared on Slack and by email. It's not a too hard read, and it's really important, I would say, really important. And you are exactly the audience for this, because you will be those who engineer the systems and who have a large degree of control if we use federated learning for good or not so good. Okay, so I would like to tell a bit more about robustness, technical robustness, and from a engineering perspective. So I'm a trained, I did my PhD in electrical engineering. When I hear robustness, I think about sensitivity analysis. So sensitivity analysis in this case means to understand or to characterize how much do the solutions of GTV minimization change when the parameters of the problem change. And the parameters, so there's a bit of unfortunate naming now, because the parameters are here, the model parameters, but this Q matrix, which contains the features, and the small Q vector, which contains the labels, these are in some sense parameters of this optimization problem. So they parameterize the optimization problem. For each choice of big Q and small q, we get a different solution. And the question is, if we change a bit this Q matrices or Q vector, how much does the solution change? Because why could they change? They could change, for example, somebody manipulates, or we get somewhat noise in our labels. Somewhat the labels of our data points, they are transported on a hard disk, and somewhat this hard disk is erroneous, fishy. So the labels get perturbed by some perturbation or noise epsilon. So how much does what's the impact of this noise on the learned parameter vectors? And to answer this, I derived here an upper bound, which you find in the lecture notes, and the proof is left as an exercise to the reader. So this would also be a good opportunity to collect bonus points if you draft me a nice proof. And this upper bound contains, again, the eigenvalues of these feature matrices, or the quadratic forms of the feature matrix, lambda max and lambda min, and the second smallest eigenvalue of the graph Laplacian. So again, we have the impact from the empirical graph, lambda 2, and to make this bound, so we would like to have this deviation small. We want to have a very robust federated learning system that, if we add a bit of perturbation, doesn't go crazy, so doesn't change the parameters too much, or the learned parameters. So to make this small, or to guarantee that this perturbation is small, we want to have a large lambda 2. And is this in line with our wishes from the previous lectures? In our previous lectures, we talked about graph learning methods. So did we want there also a large lambda 2 or a small lambda 2? Large, yeah. It's very much in line with what we want to have fast convergence, means large lambda 2, and good statistical performance, like good collaboration or pooling of local data sets, also large lambda 2. So this is all aligned. We want to have a large lambda 2. Very good. Then we have the impact of these lambdas, which are the eigenvalues of these feature matrices. And it seems that for this bound to be small, we should not have lambda max much larger than lambda min. So did any one of you see such ratios of eigenvalues? So ratio of largest eigenvalue to smallest eigenvalue of a matrix. In this case, it's this Q matrix. Did any one of you see already such quantities which involve a ratio of largest eigenvalue and smallest eigenvalue? Did any one of you have a course on linear algebra, or numeric linear algebra? So such a ratio is often referred to as condition number. In this case, it's the condition number of the feature matrices. And it seems that to have this bound small, the condition number, yeah, lambda max is by construction always larger than lambda min. So this is always larger or equal 1. So we want to have this close to 1. The condition number should be close to 1, which is the optimal. And this means a certain statistics of the feature matrices. In particular, they should be such that when you multiply them, when you form this quadratic form, give approximately an identity matrix. And this can be interpreted as being uncorrelated or white. So the features, each individual feature should be uncorrelated or statistically independent from the other features. And then using some law of large number argument, you can show that when you form then these Q matrices, they have lambda max to lambda min close to 1. So from this perspective, we want to have features that are maximally uncorrelated. And there are feature transformations that do this. They are called whitening transformations. Okay. Yeah, and of course, one component of this upper bound is the norm, the squared norm of the perturbation. So we will never make the perturbation go away completely because this factor here is always non-zero. But we can make sure that it's not too much amplified, so to say. Okay, that's about the perturbation analysis. I might skip the estimation error analysis, which is similar to the perturbation analysis, but we don't try to understand how much does the learned parameter vectors change when I add a bit of noise, so kind of an external perturbation, but how much does the learned parameter vectors deviate from a hypothetical true underlying parameter vector. And this is then called a estimation error. But this depends on how useful this model is. So do the labels and features of data points really relate like this? So is there really some underlying linear relation? But sometimes you might just postulate it. Sometimes you might just assume. Let's assume this is like this. And so the data conforms to equation 8.4. And then let's see what happens to the estimation error. And then you can again work out nice, or maybe not so nice, upper bounds on the estimation error, which involve again this lambda 2 of the graph Laplacian and the noise terms here in this linear model. So it's pretty much similar, the similar spirit of the analysis. And also the intuition or the guidance for the design choices is the same. This bound or the estimation error is guaranteed to be small if lambda 2 is large. Again, we want to have an empirical graph with lambda 2 large. Do you remember which types of graphs tend to have this property? Which types of graphs have a large lambda 2 when you fix the maximum node degrees, for example? I mentioned this a bit before. Yes, do you remember? Okay. It's, expander graphs are a good candidate for this. Expander graphs seem to be, in some situations, optimal in this sense of having maximal lambda 2 given the node, given an upper bound on the node degrees. But to make this very informal claim precise, we would need much more spectral graph theory. And I'm also not an expert in spectral graph theory. So I strongly recommend if you want to dig deeper and find out really what is the precise empirical graph structure to maximize this lambda 2 exactly, I warmly recommend the courses offered by the math department here at Aalto on graph theory. Okay. Yeah, then one thing I would like to mention here is what happens if we cannot execute this GTV minimization in its simplest form. So let me check the time. So in its simplest form, the federated learning algorithm that I have presented earlier, so it's a straightforward, a direct application of gradient descent. I mentioned then that what is nice about this gradient descent application to GTV minimization, you can execute this as a message passing algorithm. So at each iteration, each node, here is, for example, one node, gets the current model parameters from the neighbors, updates its local parameter, and then sends back the updated model parameters to its neighbors. But one nitty-gritty detail that can have profound impact in practice is that this step 3 here, and step 4, they have to be done simultaneously. And again, the paper here or the PDF is patient. I just can write down easily simultaneously. But implementing this in our computer here, our smartphones, might be very challenging to do this simultaneously, because you would need to have a synchronization. You would need to have a way to make sure all of us, all of our smartphones, know what the current iteration number is and that we are in the same iteration number. So you would have you would need some means of a global clock. Somebody who has a global clock and shares this with all of you, and you know in which clock tick K you are. And okay, here it might be somewhat possible. We might use a global clock here on the wall. But now think of how should we scale this system to all TikTok users around the world. Then it's not so easy anymore to point at the wall clock. So it might be very difficult to ensure this simultaneous, this synchronous execution in practice. And actually what we might then want, what we might face is asynchronous operation. So we might then run an asynchronous gradient method that I have sketched here in algorithm. Let's sketch it. Algorithm 8.1. So this is an asynchronous variant of algorithm 5.1, and the difference is there is no word simultaneously anymore. So it's asynchronous. But no, how do we do it? In each, we still have a global clock. We still have this iteration counter K, but this is only a notational convenience all of a sudden. This is just to write down this asynchronous algorithm more conveniently in this nice pseudocode. We don't need anymore that all the clients, all these nodes know this K, know the value of K. Rather, we say in each new clock tick, we just have a bunch of active nodes. So every time something happens, each new iteration means something happens. And whenever something happens means some of the nodes do an update. So some of the nodes have received the updates from the neighbors and do an update. And those who do the update, they are collected in this set A superscript K, A for active. And all others don't do anything. They just keep their local model parameters unchanged. Okay, so it looks very similar. I mean, the computation the active nodes do is exactly the computation that all the nodes do in the synchronous variant. But here, only the active nodes do it. And I don't make, or we need to make very little assumptions on these active sets. Basically, one only needs to assume that each node is active an infinite number of times. So there's no client which after a certain time point stops doing anything. So this is kind of the minimum requirement. And it turns out you can guarantee that this algorithm converges still. So this is called a totally asynchronous algorithm because it can tolerate arbitrarily large delays. So one lazy smartphone, let's say mine, goes to sleep arbitrarily long time, but at some point wakes up again. And it doesn't matter how long it goes to sleep, but if at some point, at some finite point, it wakes up again and contributes, and then goes to sleep again for an arbitrarily long time again, but again it wakes up. As long as every node does this, it will converge. And this is pretty amazing property of this simple distributed gradient descent method, that it's also very robust against asynchronous operation. I spare you the details of the proof. So this you can find in a textbook by one of my favorite authors on convex optimization and anything mathematical in general. I think he's Greek, a Greek guy, Dimitri Bertsekas. So there's a beautiful textbook that I have referred to here. And these two chapters, 6 and 7, they are dedicated to the analysis of this family of totally asynchronous algorithms. Any questions at this point? I mean, this is really amazing in my opinion, because I didn't do much. I just do the updates for those who are active, and the others don't do anything. They just keep their local model parameters, and those who are active, they do their updates and they share it, they spread it to the neighbors, and then might go to sleep for arbitrarily long again. Okay. Yes, in the last few minutes of this lecture, I want to discuss explainability. So one key requirement for trustworthy AI is transparency. in particular, we want to have transparency in federated learning systems. And one way to define explainability is via the following idea. So you say a machine learning method is explainable to a user. So this is important here. Explainability always refers to a specific user. That's why I call it subjective explainability. The same federated learning system might be explainable to one user, but not explainable to another user. And so when is a model or a trained model explainable to a user? And I say, or my approach to this is, it's explainable if the user can guess the predictions. So if the user can already anticipate what the prediction would be. So I measure this difference between the prediction itself. So this is the prediction delivered by a linear model with model parameters Wi. And this I call user signal. It's basically the guess. So I show the user the features of a data point, and the user should tell me what would this model predict. And if the user can accurately guess what the prediction of the linear model would be, then I say it's explainable. So explainability means that the user knows already how the model will behave or predict a given data point with features X. That's my take on explainability. And there are other definitions of explainability, but that's my take and also of some other researchers. So do you have any comments or questions to this approach? Would you define it differently? How would you quantify or measure explainability of a trained machine learning model? I mean, this is somewhat related to doing an exam, like showing the user data points with features and asking the user to tell how would this linear model, this trained linear model, predict the labels for these data points. This is like an exam. So this is similar to what I do when I want to test your understanding of the course concepts. I show you also examples. So the test set in your case would be the quiz questions in the My Courses quizzes. And then I compare your answers, your guesses, with the model or reference solutions. So that's how I test if you understand kind of some intrinsic model behind the federated learning theory. So it's somewhat similar in spirit to test the understanding of a machine learning method by letting the user predict its predictions. So this user signal here, this is the prediction or the guess of the user about the prediction that should be or will be delivered by the machine learning model. So it's not required that the user can predict the label. We do not require the user to make a good prediction of the label itself. It's only the question, can the user anticipate or guess the prediction of the model? And the model might be bad, might be a very poor model, but the user might understand it well. It has nothing to do with the prediction accuracy. So we do not compare against the true label of the data point. We only compare against the prediction of a machine learning model that I want to explain to a user. Okay, so if you subscribe, if you believe me that this is a useful measure for explainability, then why not taking it as a regularization term? So if we say this measures the explainability, and if the explainability is high, so the user can predict well the labels or the predictions of the model, so this should be small, then let's use this as a penalty term. So we add this explainability term as a penalty term to the local training error. Yes? Yes?
The user prediction is from how they
Yes. Yeah, Very good. So how can this ever work? You show the user a bunch. So let's say this weight vector or this parameter vector is the parameters of an object detector. An object detector that reads in the pixels of an image. These pixels are the features X, and you want to understand, or you want to measure how well does the user understand this object detection algorithm. So you decide a test set, this DT test set, a bunch of images, test images, and you let the user. So you tell the user in the experiment, what's your guess? Will this model detect if there is a cat in the image? Yes or no? So and these predictions are this user signal. And then you see how much do this user signal or this user guesses agree with the prediction of the model itself. Cat, yes or no?
The user not sure what's
Yes, yes. The user might have a limited understanding, yes. But the user might have a high understanding because the user might be a machine learning expert who knows the model used by this cat detector algorithm, knows about transformer networks, knows about the training set that has been used by this method. So some users might have a pretty good idea that for these test images, the model might hook on this edge and say, okay, this is a cat. But this, of course, depends on the user. So for a random, let's say for a school child, 10 years old, it might there might be a very big deviation here. So there might be this might be a large value. But for a machine learning or computer vision expert, a postdoc in computer vision, this might be very small. Well, this is just a proposal for how to measure the understanding of the user that provides us this guesses of the machine learning model. It's just one way to measure it. I mean, how would you test otherwise if a user understands this cat detector algorithm? You could ask the user, write me an expose or write me an yes. I make no assumptions about the background knowledge of the user. This is what I want to get out of this quantity. So I don't know anything about the user beside the guesses that he or she gives for these test set images. I just Yeah, I mean, that's a good question. So how you design this experiment, that delivers these numbers might actually influence the knowledge of the user somehow. If you tell the user more about the machine learning method that they should try to anticipate. Yeah.
Maybe it's not a cat. That's pretty, like, maybe it's like boom of project.
Yeah.
So they like see these pixels. Can they be biased? Like they have their own like mental algorithm going on?
Maybe, yeah. Yeah, maybe. But these are the details I try to abstract from. From me, the only thing that I see about the user or that I use to profile the user is this quantity. But yeah, of course, it depends also how you design the experiment to get these guesses. And this should be documented as a form of accountability. Yes. Yeah.
Saying what was the decisive factors in the decision. And then this kind of explanation would basically go and measure whether this explanation is successful.
Yeah, so these counterfactuals, but in the end, they're also a way to somehow tell the user or inform the user about how this mapping from features to label is. So it's again one way to tell the user or to explain the user the function edge. So this hypothesis, what's this function? And so this tests basically if the user can replicate the function values of this hypothesis for specific data points for which we know the features. Yeah, so maybe I let it sink in for a while. And yeah, I would be happy to hear more comments than on Slack or by email, because this is really current research in my group, and would be happy to also start a collaboration if this is also along some of your research interests. Yeah, then so let's assume this is a good measure for explainability or lack of explainability, actually. So if we want to minimize the lack of explainability, we should penalize it by adding it as a regularization term. And if we again use linear models, it turns out that this whole expression here turns out to be a quadratic form, a convex quadratic function in W, which is parameterized not only by the labels and features now, but also by the user signals. So computationally, we end up again with minimizing a convex quadratic function. And all the analysis of gradient methods for convex quadratic functions also applies here for subjective explainable federated learning. Okay, that's it for today. You find now the overview of the coding assignment in the end of this lecture, of this section in the lecture notes. And yeah, please remember the deadline is not on Sunday, but on Sunday in a week. So you now have a bit more time for this quizzes. Yeah, thanks for your attention. Are there any questions at this point? Yes.
I was like wondering what the user explained or that like someone can provide the explanation, like if you're a resource, you
Yeah.
can say that okay, these are the way it is.
Yeah.
But like if someone can do that, isn't it enough? Okay, maybe there's some use case where you want the users to know that, like
yes. Yes, so very good point. So again, this explainability is subjective. So we might not need at all this penalization because the federated learning engineer or the system designer knows or has a very good understanding of what the model will learn. But the key thing is that the user, and the user can be a 10-year-old kid, should also have some understanding, or we should also ensure some explainability. And this is what this key requirement also touches upon. We must ensure explainability for all kinds of different stakeholders. And the stakeholder can be the random user, teenager of a TikTok app, or can be a professor in machine learning. Then, of course, you have different levels of explainability. But this is a way to ensure explainability in an automated fashion. I mean, the premium solution would be to invite this teenager who uses TikTok to a one-day seminar with me where I explain all the details of machine learning to him or her. And then he has a better understanding. But this is very costly. I mean, of course, for me, it would be beneficial monetarily if somebody pays for it. But this is something that can be completely automated. And to some extent, I might make myself also redundant, because you can then optimize the predictions. Like, let's say the predictions could be, what's the best design of a lecture that I give today in order to optimize your understanding of federated learning. And this understanding is measured by the error on a test set, like a real test, an exam. So this would be kind of the let's say the long-term future solution for education, for automated education. Okay, any other comments or critique about this approach to explainability? Yes.
Could be like an average or something to have like some statistics in the whole concept to give you a good picture of the course design.
Yeah.
But how would you like? What do you think about that in practice? Because this is like one user.
Yeah, we would learn. So one user is this superscript I. We have a separate model for each user. So we train a separate teacher for each one of you. So basically, I would be cloned and optimize my teaching to your background. So if some of you have a background on spectrograph theory, my clone would do more details on the spectral, on the analysis of this federated learning algorithms. If others of you have less, another clone would optimally bring you up to speed in basic linear algebra. So these models here, these are, so to say, personalized models. And we measure the subjective explainability for each user. So there's a different subjective explainability level for each user I. Yeah, I mean, I have also thought about this because it's challenging to implement this in an experiment. So what could be a user study? And one user study, or it's very related to this personalized learning apps. So kids nowadays have these learning apps like Duolingo, I know, coincidentally. So, I mean, that's the same goal or the same problem setting as an explainable machine learning. You want to guide the user, or you want to train a model such that the user optimally understands it. Understands something. In education, you want the user or the school kid to understand linear algebra. So you make predictions about what to show the student, which examples to give him, such that, or her, such that in the next exam, he or she will optimally predict the answers, the correct answers. So in an exam, these predictions would be the predictions for the correct answer, so to say. And the user, in this case, the student, provides his or her guesses for the correct answer. Okay. Yes. I think this is pretty much open. So there's also, as I said, there's no consensus about how to measure explainability. I don't know any document by the European Union where they define a measure for how to measure explainability or how to measure transparency. I mean, there are measures for communication, like bit rates. How many bits can you communicate over this channel? Or there are measures for the weight. How many grams does it have? So for certain quantities, we have well-defined procedures to measure it, but explainability, I didn't see yet an official regulation that tells you have to measure explainability like this. So, but let's see, maybe I'll try to lobby a bit in Brussels. Yes.
There's obviously that is but then there's also the problem that there isn't possible to understand. And in order to what you understood, do you want to sue us?
Yeah. Yes. Any other questions or comments about trustworthy federated learning? Okay, if not, then thanks for the attention and see you after the Easter break. We will then have, not sure, I think the next lecture is then a guest lecture by a professor from Italy who is expert on privacy preserving machine learning. Okay, thanks and have a nice evening.